Just sometimes use reviews.
Okay, but I missed yesterday, but I missed econ.
That's fine. You keep right on missing those classes. Just be here. All right. So, today we're returning to conservation of momentum.
I thought you meant like cons, like pros and cons. I'm like, oh, they're bad. Okay.
Depends on how you look at it, I suppose. This is physics. There's no value judgments, right? All right.
Everything is equally unvaluable.
Wait, before we get started, no, this is actually like,
Hey, Josh.
Hey, Josh, what's up? The quiz was hard.
All right, so if you take the second law, which the second law of motion says, good, that the net force equals ma, and therefore the net force times time equals the mass times the change in velocity, which you'll recall, this side is impulse, and this side then is the change in momentum, right, because momentum is in v. If we take that and we couple it with the third law, which is
Every action has an equal opposite.
right, the equal and opposite reaction, that there are action-reaction pairs for all forces. And again, just as a way of reviewing, if I have a block of mass m sitting on a table, then somebody give me an action-reaction pair. Okay, be more specific. What? It's on a table. No. This is a common mistake, and that's why I wanted to bring it up and clarify. The action-reaction pair is not the force diagram. The force diagram says that mg is pulling down on the block as hard as the normal force is pushing up on the block. But that's not the action-reaction pair. Because, is that always true? If I remove the table,
normal force is opposed to,
then
there's normal force coupled with the circuit that is on the opposite direction.
yes. So the normal force is what? This is the table, the force of the table on the block, the box. So what would the action-reaction pair be for that? The force of the table on the box is equal and opposite to, good, the force of the box on the table. Is that mg?
In this case, because there's no other outside.
No. It's equal to, but the force mg is not the force of the box on the table.
Because if you're pushing down, it's like
The normal force is both ways.
The normal force, right, is the table on the box, and then there is a force of the box on the table that's equal and opposite to the box, I mean to the normal force. See, the problem is, this is a force diagram of just the box. What if I change colors and draw a force diagram of the table? Then we have the weight of the table plus the weight of the box. There's the force of the box. This guy right here is the one that's equal and opposite to the normal force. And then there's also, what? What is the... Good. The ground. The force of the ground, right? The normal force of the ground on the table. Okay? So, be careful with your action-reaction pairs. It's easy to slip into confusing two balanced forces acting on one object as an action-reaction pair. But if it's action-reaction pair, it's always going to be on different objects. It's one guy pushing on the other, and the other pushing back. Okay? So in other words, action-reaction pairs never show up on the same force diagram, because the force diagram is only talking about forces acting on one object. Yes?
So this would be the normal, not the normal force, but the force from the table pushing up, and the weight of the box going down.
Yeah, your action-reaction pair here is the normal force, which is the force that the table is exerting on the box, and this guy, which is the force that the box is exerting on the table. There's your action-reaction pair. Table on box, box on table. Alright? Now, when I combine these two laws, I can think of a scenario, for example, of sphere A and sphere B colliding. And if the mass of sphere A is larger than the mass of sphere B, then when they collide with each other, tell me which relationship what symbol belongs there. How do the force of A on B and the force on B on A relate? They're equal?
And I wrote it. But is he playing with us or is he passing?
Next level.
Is it the voice trick or is the voice trick trick?
The double trick with the eyebrow raise. It's like a double trick. Everyone knows what I'm saying.
What goes in that circle?
Equal reaction.
So you think, even though the mass of A is quite larger than the mass of B, that there's an equal sign here? Well, not because of that, but because of right here.
So it was the voice trick trick.
Yes, it was the voice trick,
So
trick,
that's
trick.
where we got it now.
It's equal. Force A on B cannot be any greater or smaller than force B on A by Newton's third law. It's the whole...
We're good. No, because I'm anchored in right here.
You almost went over, you know it. It's the whole punching the hole in the piece of paper thing from last year, right? You can't punch a hole in the paper with your fist because you can't push on the paper harder than the paper can push back, right? You don't remember that demo?
No, I remember, but you
Okay.
think you can't push on paper harder than paper can push back.
So we like shot a
Paper's
bullet.
not exactly just wrong. I mean, Jacob, sometimes.
Yeah, what if the physics of something going through or something? Like a bullet, like you said. A bullet going through a paper.
What about it?
How can your fist not break paper if you can break a wall? Like drywall.
Because the drywall can push back hard enough to get to its breaking strength.
So this can't push back hard enough to get this breaking strength.
Right.
So it's not that you can't push harder than it, it's that it can push as hard as you.
And so the total
The same.
How is that the same?
I can't push any harder than it can push on me. And since it can only push so hard on me, that's only how hard I can push on it.
So you can push real hard. Ah, this is so weird. Like, I know what you're saying, but the way you're saying it just makes it sound wrong.
So if you shoot a bullet at a piece of paper.
Good, mission accomplished.
Wait a second. If you shoot a bullet at a piece of paper, it will just punch it down.
Ah, now you're getting ahead of us, right?
It's gonna bounce off.
Because that's not just the force, that's the pressure as well. So. Yeah. All right. Well, see, what you did right there is now, by introducing this, you're exerting a force on the paper to allow the paper to push harder. Exactly. Exactly. Yeah. All right. So now A comes in and hits B, and we said then that the forces on them are going to be equal. So who's going to push longer? Is A going to push on B longer or shorter than B is going to push on A?
Trick question.
Well, yeah, clearly they have to. If by pushing we mean they're going to interact with a force on each other, then as long as they're in contact and one's pushing on the other's going to be pushing on one. So by those two is where we get this notion of the conservation of momentum. The fact that if they experience the same force for the same duration of time, then they're going to be causing an equal change in momentum. Now, that doesn't mean that individually they experience the identical change in momentum, but the change of the momentum of the system has to be zero. Yes, it is. The sum of all the momentums before has to equal the sum of all the momentums after.
And momentum's a vector.
Yes, momentum's a vector because it's mass times velocity, and velocity is a vector.
So that come out.
Absolutely.
As opposed to last year.
Yes. Last year we kept it simple. This year we get to take a step farther. Okay? But we'll start where we were last year, right? We'll be nice at first. And we'll say that if I have, let's call it a 3 kilogram ball, it's going 4 meters per second in this direction, and it's going to collide with a 2 kilogram ball that's initially at rest. And then after the collision, if the collision slows the 3 kilogram ball down to 2 meters per second, then what's the final speed of the 2 kilogram ball? Either one. I just asked for speed, but you could give me its velocity because we know the direction of the initial velocity. And so the sum of all the initial momentums has to equal the sum of all the final momentums. So this guy is mv initial, m1 initial v, plus m2 initial v is 0, so his momentum is 0. And we know that has to equal m1 times his final velocity plus m2 times her final velocity. Well, that's just 12 kilogram meters per second. And this is 6 kilogram meters per second plus 2 kilograms times final velocity. So combine like terms and then divide by 2 kilograms, and I get the final velocity is 3 meters per second to the right. The final speed, 3 meters per second. The final velocity is 3 meters per second to the right.
But doesn't the opposite direction?
If we had indicated it, yes. I mean, in our picture we indicated the direction, and since we're not drawing it down here, I guess we did draw it in that picture, so yeah. Okay? That's too easy, right? Well, what you're going to do in your lab next time is you're going to have something like this, a mass of M, we'll say, and you're going to have another mass identical M that's initially at rest. And we're going to say, if we know its initial velocity, then we should be able to confirm that if this one hits that one, causing that one to go that direction, and this ball, when it hits it, goes that direction, then is momentum conserved? Yes, momentum's always conserved. Incidentally, side note, types of collisions, this should be reviewed. Good. Elastic, inelastic, and perfectly or totally or completely inelastic. And which of those is momentum conserved? All of them. And which of them is kinetic energy conserved? No. Elastic is the only one where kinetic energy is conserved. Let's come back here. Was kinetic energy conserved in this collision? Well, the kinetic energy here is 1/2 mv squared, which is, what, 24 joules? Right? 16, 8 times, yeah, 3. And this is 0 joules. And then after, this is 1/2 mv squared, which is, what, 6 joules? And then this one is 3 meters per second, and 2, that's 9 joules, right? Hello? Is that right?
Yes.
So was energy, kinetic energy conserved? No. So what happened to all that energy? It just disappeared.
External forces.
Good. Energy doesn't just disappear. It was lost in the form of heat, friction, possibly air resistance, sound, right? The heating of the balls as they collide. Okay. So, elastic collisions are the only ones for which kinetic energy is conserved. Now, what's special then about perfectly inelastic collisions?
They stick together as one item.
Good. You end up with one mass. You start with 2 and you end up with 1. So it's the railroad cars colliding. It's the clay spheres sticking together, whatever. Okay? And inelastic is everything in between. All right? So this is an example of an inelastic collision. Now, back to your lab. What we're going to then do is we're going to say, hey, if this is the momentum vector after the collision, that means it's the mass times the velocity vector. And therefore, that combined with the momentum, the final momentum vector of this one, which is mass times the final velocity vector in that direction, then what should be true about the horizontal components of the momentum vectors? They have to be equal, because what was the initial momentum in the vertical direction over here? 0. Therefore, that guy has to equal that guy. I should have done the components by color. I should have done this. That should be red. And it's not going to let me circle that one. That should be blue. Oh well. Oh no, I'm sorry, not that. That should be blue. Right? Because the reds are going to be equal. And then what's going to be true about the blues? Are they going to be equal?
Not necessarily.
No, not necessarily. They're going to add up.
They'll add up to be equal to the beginning.
Exactly. So this guy's x plus this guy's x have to equal what it was before. Alright? Now, what you've got to be careful about when doing these problems is you can't just say the velocity, you can't just take this initial velocity and these two final velocities and say that that initial velocity equals that velocity times that, plus that velocity, right? Because is velocity conserved? No, it's momentum that's conserved. So be careful. Okay? Alright, so I'm going to give you a problem to work for homework. We've got a ½ kilogram mass that's traveling 2 meters per second. When it collides with, we'll keep it simple for now, another ½ kilogram mass that's initially at rest. If after the collision the mass that was originally at rest moves off at a 40-degree angle going 1.5 meters per second. Then I want to know the final velocity and that might not even be the right direction, the final velocity of the original mass. Yes. So again, treat it kind of like we did force vectors. We know that there was an original momentum vector that had all horizontal components, right? And so the horizontal component of this plus the horizontal component of that have to equal that original horizontal momentum. And then I also know that the vertical components, because the initial vertical momentum was what? 0, then the final momentum, vertical momentum, has to equal 0. So since they're in opposite directions, they're going to be equal in magnitude in opposite directions, so I can find what they are. Okay? Alright, have fun.